Here I'm going to calculate the Laplace transform of e to the negative t squared. I'll need to use a couple of results that have been discussed in other MathsCasts. I'll write these down first. To begin with, I need you to know the following integral result. It's the integral of e to the negative x squared dx from 0 to infinity. It has the value root pi over 2. I've talked about that result in a MathsCast with a title something like the integral of e to the negative x squared using double integration. If you don't know about double integration, you might find some of that a bit hard to understand. In that case, I ask you to accept this value. In a separate MathsCast, I discussed a function called the error function, erf of x. I discussed that in the context of the normal distribution in statistics, but it's a function which stands in its own right. I'll write down erf of x now. Notice it's actually the same integral as before, except that now I've called the integration variable u, and the variable x, on which the function depends, appears in the top limit of the integral. The factor 2 over root pi is there in order that erf of infinity is equal to 1. You can check that yourself using the two results that are here already. There's one other function that I want to mention, and that's called the complementary error function, erf c of x. It's defined in terms of erf as just being 1 minus erf of x. Armed with these three results, we're now ready to look at the Laplace transform. Let's write it down. It should be L of e to the negative t squared. We'll take the Laplace variable to be s as usual, so we want the integral from 0 to infinity e to the negative st times e to the minus t squared dt. That will be a good convergent integral because the exponentials will all get very small as t gets large, assuming as always that s is positive, of course. Okay, what can we do with that? Well, I suppose the natural thing to try to do is to combine the exponentials. So e to the negative t squared plus st dt. If it was e to the minus something squared, I'd be able to use the very first result above here to evaluate it. But at the moment it's not a square in that exponential. So let's do what we normally do when we would like to see a square with a quadratic present. We complete the square. So that's going to be e to the negative, and it'll be t plus s over 2 all squared, minus s squared over 4 dt. Now I'm going to break up the exponential and take the e to the power and look at two negatives, one here and one here, so that'll be e to the plus s squared over 4 e to the minus t plus s over 2 all squared dt. Now the integration variable is t, and s squared over 4 doesn't depend on t, so it's effectively a constant, so we can take that outside. Now I see e to the power of minus something squared, which is what I'd rather like from the point of view of using my first integral up here. The trouble is it's not just x, is it? It's t plus s over 2. Why don't we make a horizontal shift, or in other words change variable, and let u be t plus s over 2. Then it would follow that du is the same as dt. Furthermore, when t is 0, that's the bottom integration limit, u must be s over 2, and when t gets very big, that's the top integration limit, u also gets very big. So now our integral becomes e to the s squared over 4 still at the front, integral still infinity on top, but now not 0 for the bottom limit, but u equals s over 2. and then inside e to the minus, but that's now just u squared, isn't it? And dt is the same as du. Now that doesn't quite look like our top integral, does it? Because the top integral that I wrote down right at the beginning has 0 for its lower limit. So why don't we write this slightly differently? Still the exponential at the front. Let's put 0 on for the bottom limit. But now what I've written is not quite right, because I've included some extra bits in the integral, and I need to take those off. But I can do that by taking 0 to s over 2 of e to the minus u squared du. And now, integral 0 to infinity e to the minus u squared du, well, it doesn't matter whether the variable is called u or x, it's that same integral that we had right at the top. It's just root pi over 2. So that's e to the s squared over 4, and the first term is root pi over 2, and then minus, and now what's this other one? It's the same integrand, but it's 0 to s over 2. And actually that's the error function, isn't it? Except that we have to change the x to s over 2, and we actually have to get rid of that factor at the front, 2 over root pi. So we need to cross multiply that. So I urge you to check, but that gives us root pi over 2 times the error function of s over 2. And if we take out the root pi over 2 as a factor, and the exponential is still there, and now we have 1 minus the error function of s over 2. And we can tidy that up by recognizing that 1 minus the error function is just called the complementary error function of s over 2. So there is our Laplace transform for e to the minus t squared. It's root pi over 2, e to the s squared over 4, error function complementary of s over 2. I urge you to check this on Mathematica. Mathematica knows lots of Laplace transforms, and it will confirm this one for you.